Here's the story of Mr. Wade's evolution. I taught mathematics at this institution, but then came March. They postponed school. COVID-19 was playing us like a fool. I snuck back in and taught some AP, but they locked up the building and cut the AC. I got frustrated and wrote some sick rhymes. I filmed a rap video just to pass time. I started teaching lessons from my house in Brentwood. Oh wait, you're not supposed to see my real house. I started teaching lessons from my house far away, but I missed writing on a board every day. I talked to my friend Steve Smith, computer hacker. We had to find a whiteboard and he's no slacker. We looked around the city, we finally scored, and now I'm back teaching from a dry erase board. Now we're off Schoology, every single grade, and that's the story of the evolution of Wade.
Now in Mr. Wade's curriculum, this is lesson 3-1 for BC students. So we need to start applying the derivatives in other ways, fun and creative ways, while still getting better at our derivative skills and looking for clues to say, oh, I'm supposed to be taking the derivative. All right, so we start off with a problem that resembles a problem in chapter 2. Remember that biggest rectangle, maximum rectangle we could squeeze under a curve? Okay, very similar. We've got the largest rectangle that you can squeeze under y equals 48 minus 4x squared. But as long as it stays above the x-axis, it's fair game. So, no graph this time, you have to do your own graph. All right, so, thou shalt know thy graphs from integrated 3. Otherwise, you're going to be toast in calculus. So, x squared, parabola, negative x squared, concave down parabola, 48, shifted up 48, right? Isn't that the same as a plus 48 at the end? So these are the things you have to know from integrated 3. Okay, there's my 48. So, upside down parabola, and instead of bouncing off the origin, we're going to shift it up 48. You need to be able to graph that in like 2 seconds in a calculus class. Okay, we're done with basics. Let's go to calculus. Above the x-axis, but below or inscribed inside this parabola. So inscribed means that the parabola surrounds it, the rectangle fits inside of the parabola, like that, okay? Now we need some dimensions. Okay, first key right here. We do not know what this point is. This point could be just about anything, all the way to whatever this x-intercept is for the parabola. Doesn't really matter, but let's call it x because it could be anything, okay? Now, over here, this is a perfect mirror image because the symmetry of the parabola, even though my rectangle does not exactly look like it has symmetry, this is negative x because it's a mirror image. All right, so x is unknown. Where do we position x? How far do we drag x so that we get the biggest possible rectangle? Because the rectangles are going to get bigger and bigger because they start low and flat. And the more you move this x out or in, it's going to grow bigger, and then eventually it's going to get so tall and skinny that it becomes a smaller rectangle. So we want the maximum rectangle. All right, so the other key, this coordinate right here, it's above x, so it is x comma something because it does line up with x. The y coordinate, what's the y coordinate? We don't know, but wait a minute. Isn't the y coordinate always equal to the equation? Isn't this where you get y coordinates? So isn't any point on the parabola, including that corner, x comma 48 minus 4x squared? That's the key. xy won't really help you, but that's what it comes from. X comma equation will help you often in calculus, okay? Largest rectangle. Start to interpret from English to math. Largest, maximum, derivative, right? Maximum, minimum, increase, decrease. Take a derivative. So largest means max or derivative. Derivative of what? Derivative of the parabolic equation? Well, normally in the past, we simply took the derivative of the equation. But be careful. It's not the maximum of the parabola, it's the maximum of the area. We need an area formula for the rectangle so we can maximize that. So area of a rectangle, let's scoot this out for a second. Area of a rectangle is base times height, or length times width, okay? The base of this rectangle is, that's x, that's another x. X plus x is 2x. So your base is 2x. Your height, what's your height? A height in math is a y coordinate. And the upper y-coordinate of the top corner, didn't we say it was the equation that I just erased, trying to make some space here? So isn't the upper y-coordinate 48 minus 4x squared? That's how tall your rectangle is going to be. Only as tall as the parabola will allow it to be, okay? So x plus x is 2x, and equation is the height. Instead of doing the product rule, which you could, but it would be really difficult, I would distribute the 2x because somebody left the lock off the gate. There's no power on the parentheses stopping us from distributing. Let's distribute. Double 48 is 96, x. 2 times negative 4 is negative 8. X times x squared is x cubed. There is the equation for all the infinite rectangles you could squeeze under this parabola on top of the x-axis. Who is the largest? Real life maximum, a prime, derivative of the area. A prime, 96x becomes 96, minus 3 times 8 is 24x, drop the power by 1 to the squared, and then of course it's like doing our case 1, case 2, case 3, only a case 1 here, just set it equal to 0, okay? Solve that. Oh, I don't want my x's to be negative. Add that thing over to the other side. 96 equals 24x squared, much better. Divide both sides by 24. X squared equals 96 over 24. I bet Mr. Wade gave you a perfect square because I always try to give you, nice answers on non-calculator tests. I wonder if 24 fits into 96. Well, here's a clue. How did we even get 96 in the first place? Wasn't that 2 times the 48 that gave us 96? Put 96 in disguise as 2 times 48. Put it back to what it used to be, okay? 48 over 24, look at that. 48 over 24 is 2 times the other 2. That's how you do this stuff quickly. It is 4. X squared equals 4. Thanks for the perfect square, Mr. Wade. You're welcome. X equals plus or minus 2. Okay? Now, real life, maximum, minimum, increase, decrease. Do you need a first derivative test? Normally those words say do a first derivative test. You could do one, but you're wasting time. If it's a real life equation, a real life problem, you can use common knowledge, use logic, okay? Now, positive 2, if I set x out here at positive 2, that's got to be the biggest rectangle. It can't be negative 2. That would be moving this back the other way. It would flip-flop the entire rectangle backwards. That can't be the actual answer, okay? So, positive 2, logically, x equals positive 2 is going to be the winner. So you can just kind of eye your so-called critical numbers, critical points, and figure out the winner. So x equals 2 is apparently the best place to position this right here. So that must have been negative 2 in reality. And now you've got a fixed rectangle that's going to be the biggest. Again, they use this in architecture. They use it in structural engineering. It's all kinds of important things. So now just make sure you read the question. It didn't say give me the x. It said give me the area of the largest rectangle, right? So to find the actual area of it, we take 2, we plug it back into the base times height area formula, okay? Remember what I've been saying recently in these lessons. Could you plug the 2 into the 96x minus 8x cubed? Sure, but don't I always say that the factored form is better, more efficient, easier? Always go back to your factored form, okay? I'm going to put the 2 here instead. So 2 times 2, the first parentheses is 4. Let's put this over here. Area equals, that's a 4. 2 squared is 4. 4 times 4 is 16. And 48 minus 16 is 32. This is easier than if you had put the 2 in here, okay? And then 4 times 32, 4 30s makes 120, plus 4 times 2 is 8. 128, or you could do a double-double as we've done before. 128, square whatevers. They didn't tell us, so we don't have to tell them. Square inches, square feet, square miles, okay? 128, done with that one. All right, let's go over here to a little bit of trivia and history, which I love, so that you really understand and appreciate this stuff. And then we'll go on to an application. So, square roots. You all know the square root of 144. We do our perfect squares all the time. The square root of 144 is 12. You probably knew that in 3rd grade. Because what? Why is the square root of 144 12? Let's remind ourselves. Isn't that because 12 times 12, or 12 squared, gets you back to 144? Okay, great. Now let's go a little bit harder. What's the square root of 145? Well, there's not really a whole number times itself that could get you back to 145, right? Wouldn't it be a little higher than 12? Because 145 is a little higher than 144. So what would you say? 12 point blah, 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 right? 12 point something. Okay. Isn't that an irrational number? If it's not a perfect square and you take the square root, you get an irrational number. Like pi, it never repeats, it goes forever, there's no pattern, okay? So, what is that number and how do we even get it? All right, so let's think about this. How would you get the square root of 145 if I told you to go do it right now? You go to your calculator, type it on the calculator. But wait a minute, who programmed the calculator? How do they know that 12 point whatever times itself is going to be exactly 145? I mean, somebody has to program the calculator or we could have never figured this out in the first place, right? So, we take a little trip to Europe. Let's see how well you know your geography. This works a lot better in a class where there are people present live. It doesn't work as well over a YouTube video, but I usually ask my classes, does anybody know what European country has Sofia as the capital city? And there's always one person that knows. Let's see if anybody knows at home today. Hopefully somebody said it. Sofia is the capital city of Bulgaria. Of course, okay? So, here's what happened in Sofia, Bulgaria. This Elka company came up with the Elka 6521 in 1965. What's so special about it? Well, it was a big, bulky calculator, way bigger than the calculators we use today, that's for sure. Now we have calculators on our phones. This was the first calculator ever made with, guess what? Square root capabilities. It also had addition, subtraction, multiplication, and division. So only since 1965 have you been able to type in 145 into a calculator and hit the magic square root button and just take it for granted and get the decimal, the irrational decimal 12 point something that multiplies by its 12 point something self to get you back to 145.0. We've taken it for granted ever since. But wait, the blanks estimated square roots to 5 places accurately as far back as 1800 BC. Matter of fact, there's a stone tablet that is kept at Yale University right now that proves that they could do square roots that far back. Who is carving into that stone tablet? Remember what I said? If you go this far back into the BC era, there are only 2 possible answers in this class: the Babylonians or the Egyptians. Those are the only 2 races of people that were that advanced back then. Babylonians was the answer last time. Egyptians is the answer this time. So the ancient Egyptians, who were the same ones who built the pyramids, were actually able to estimate square roots. But wait a minute. How did anybody estimate the square root of 145 before 1965? Like, how is that even possible? Okay, well, let's find out. And to do so, we'll do one of my favorite problems of the first semester. This is a gem right here. It's so fascinating. So once calculus debuted in the late 1600s, we could really up our game on estimating square roots, cube roots, fourth roots, and everything else. Okay, estimate the square root of 102 to the nearest 10th with no calculator. Did you ever believe you'd be able to do this in high school? You can actually estimate a square root of something? Okay, step 1. What are we talking about here? Square roots. So I want us to draw the y equals square root of x graph. If we were doing cube roots, you would draw the cube root graph. Once again, from integrated 3, know your graphs, and you can be very successful at calculus. Square root of x. Isn't that parabola on its side, top half only? Remember this whole game back in integrated 3? Origin, sideways half parabola, that's y equals square root of x. Okay, now, we're trying to take the square root of 102. 102 is the input, or the x. So I'm going to mark that on the x-axis, just call that 102. 102 is the input. If you take the square root of it, the output is the y coordinate. So let's go up here until we hit the graph. We'll put a dot. Isn't that 102 comma square root of 102? But I don't know what the square root of 102 is, right? But that's what we want. We want the output or y coordinate. Now, see down here where it says pick your point of tangency? Okay, so the strategy is draw the square root curve, pick the point that you're trying to take the square root of. Now pick your point of tangency. Yes, we are going to do a tangent line equation. What do I pick, Mr. Wade? Pick something that you do know the square root of. What's something very close to 102 that you can take the square root of? How about 100? Excellent choice at home if you said that. Let's mark 100 on the x-axis. We're going to go up to the curve, and I'm going to write the point 100, comma, not square root of 100, because we know what that is. Let's just put 100, comma 10, right? Okay, you know what the square root of it is. So that we do know. The square root of 102, we don't quite know. Okay, now, we're going to find the tangent line equation. Let's draw a tangent line here. Draw your tangent line to the point that you specifically know, not to the one that we don't quite know. So draw a tangent line. I want you to picture, remember at every point there is only one unique tangent line, so kind of picture it like right in there. And let me get ready to try to make this as accurate as possible. And, okay, you artists in the class will do a lot better than I did. But that line skims the 100, comma 10, skims the square root graph. Tangent line. Now, let's find the equation to that tangent line because that's the key. If you see the word line in any math class ever, line, three things, x, y, m. Those are the three ingredients of every line. X, y, m. All right, what's the x and the y on the line? The 100, comma 10 is not just on the curve, it's also on the line. The 102, comma square root of 102 isn't even on the line, so you wouldn't be writing it in the line equation. The point's on the curve, right? So pick the point you know on the line, and then give me the slope of that tangent line. Oh boy, well, back in the old integrated classes, you could have 2 points and do rise over run. Well, you don't have a second point on the line. You only have 1 point on the line. Derivative. Derivative is the slope of any tangent line. How about that? Let's take the derivative of the curve, which is the derivative of y equals square root of x. Let's do that off to the side here. So we'll do aside. Y equals, isn't that just x to the 1/2, right? If you take the derivative of any curve and plug in the point of tangency, you can find the slope at that point of tangency. You want to talk about real life science and math, by the way? Major right there. Okay, y prime equals 1/2 to the front. Base stays the same. Subtract 1 from the exponent. 1/2 minus 1 is -1/2. No chain rule necessary, but the derivative of x is times 1. It's invisible, but it's there. And then finally, who's on top? 1 is on top. 2 is on the bottom. X is on the side, which means top, but the negative sends it to the bottom and becomes x to the positive 1/2. There we go. Now, if you wish, you can rewrite that as 1 over 2 squared of x. I mean, same thing. Maybe better as a radical, I think. So there is your derivative. That is your formula to create any slope at any point on the square root curve. Okay? We want the slope at x equals 100. So we take our x of tangency, we put it in there, and the slope of this tangent line is 1 over 2 times the square root of 100. Another real-life application of the derivative. 1 over 2 times 10, that is 1/20th. I am not surprised that that is a very small number. Isn't slope rise over run? If you go up 1 foot, or up 1 foot, and you run 20 feet, isn't that a very shallow sidewalk? Rise 1, run 20, very shallow. Well, yeah, the tangent line is very shallow because doesn't this square root curve really level off? It never goes perfectly level, but it really levels almost horizontal, but it's ever rising, isn't it? but it gets so almost horizontal that the tangent line gets almost zero slope. Not ever, but very close. So we already have very small rise over run when you get to 100. Makes sense. Okay, so the equation of my tangent line is y minus y1, which is 10, equals m, 1/20th, times x minus x1, which is 100. So that's a little rehearsal from the last test to get better at tangent lines. Now, what the heck does the tangent line have to do with estimating the square root of 102? Here's the connection right here. If I plug 102 into the tangent line for x, wouldn't it give me the y coordinate at 102 on the line? Notice I'm putting it into the line equation. So it would give me the point that's on the line. Here, let's get a close-up of this. So plugging 102 into the line equation would give you the y coordinate above 102 on the line. Look how close that is to the 102 point on the square root of x. So whatever our y coordinate is for that point on the line is going to be just above the square root of 102. Because remember, y coordinates are heights. So it's going to be a little higher, but you see how close that is, right? Probably closer in real life. I mean, I'm just kind of doing a crude sketch on the board. So take the number that you want to estimate the square root of. Plug it into your tangent line instead. Because we're not going to be able to plug it into the square root graph. We don't know what the square root is. Y minus 10 equals 1/20th, 102 minus 100. So I put in 102 to the line. 102 minus 100 is 2. And 2 times a 20th is reducing to 1/10, doesn't it? And I'm going to add, I'm trying to solve for y here. I'm going to add 10 to the other side at the same time. Okay? And as a decimal, because it did say the nearest tenth, right? We're trying to get to the nearest tenth. Isn't 1/10 0.1? So you end up with 10.1 as your final answer. So in conclusion, the coordinate on the tangent line equation is 102, 10.1, which is a slight overestimation for the actual square root of 102. Now I'm curious as a cat. It's probably why my friends keep calling me Whiskers, but I went to a calculator and I did the square root of 102, since we can now take the square root button for granted these days. And the square root of 102 was about 10.0995. Well, I'll be darned. It's irrational and goes forever, but isn't that about 10.1? Well, how about them apples? Now, you might realize this. The farther you get away from the 100, the worse the approximation gets, because the tangent line is going to take off and the square root curve is going to keep leveling. So they're getting worse and worse and worse. But as long as you're in this local area around the 100, you're going to get a pretty darn good estimation. That is amazing. It is so clever. It is so cool. The first time calculus students actually do that problem with me, it's just fascinating. All right, so you just approximated a square root. Now, let's take it one more step. Before we go to the last problem, I want to point something out. In this problem here, why was it an overestimation and not an underestimation? Is it because the square root of x graph is forever increasing? It is increasing. Is it because the square root of x graph is concave down? Does everybody see how its curvature is concave down, not concave up, right? Okay, so the double derivative would be negative forever, in other words, right? Concave down, last test. You know what? Some of you have already thought of it at home, I'm sure. It comes down to the concavity, not the increase or decrease, okay? If a curve is concave down at the point of tangency, any estimations in the local area will be a little higher. If you have a concave up curve and you do a tangent line, at the point of tangency, the line is exactly the curve. Around the local area, the points on the line are very close to the curve. But of course, the farther you get away from the point of tangency, they start to deviate and get farther apart, right? Only in the local area is it accurate. But if it's concave up on the curve, Your tangent line is giving you underestimations for the actual point on the curve, all right? So it's all about the concavity. So that logic brings us directly to C. All right, last problem. F is concave up. Let's draw a little example. F is a concave up curve, okay? Great. On an interval containing the point of tangency, okay? So let's see, let's have a point of tangency. Let's just pick a random point and we'll just pick a tangent line, kind of like what I drew over there anyway. On an interval, so let's narrow this down to like a little interval, a little window. Remember that's like a vertical line and a vertical line at two different x coordinates. So on a window, on an interval, a very small interval, containing the point of tangency, if f is concave up, what can we say about the local linear approximation? Whoa, that sounds fancy. Mr. Wade, what's a local linear approximation? It's what we just did on the other board. The tangent line can also be called in that situation the local linear approximation. Why local? Because when you're in the vicinity of that 100, 10, you get accurate answers. Remember that? Local means in that vicinity. Linear. Oh yeah, we used a line to approximate the values of a square root curve. So local linear approximation is using the tangent line to approximate pretty good square roots in the local vicinity. Okay, but what if the curve is concave up? Now what? What do we know about f? The local linear approximation of f must be blank compared to the function's value. What's the function's value? What does that even mean? Oh, the function's value. That's the actual outcome or a y-coordinate of points on the parabola, or this isn't necessarily a parabola, but whatever concave up curve this is, right? So the function's value, oh, remember last test, last chapter, value always means y-coordinate, remember that? The function's value are the actual y-coordinates on the concave up curve. What do we know about the local linear approximation and those outcomes? So let's go directly beneath it because we're looking at like the same x-coordinate vertically. So the local linear approximation that's giving us a pretty good answer for the curve's y-coordinate, it's a little off. That is blank compared to the actual curve's y-coordinates. Isn't it under? Isn't it lower, right? Because it's all about the concavity. So when they ask this on the AP exam some years, what they want you to say is, oh, if the curve is concave up, then my tangent line, i.e. local linear approximation, is less than, isn't it? It's less than the actual function's y-coordinates, okay? Less than. Now don't forget this. Or, I didn't make my blank long enough. Hopefully yours is. Less than or what? At the point of tangency, the tangent line does not estimate the curve. It is exactly the curve. Less than or equal to, just because the point of tangency is the exception there. Less than or equal to the actual concave up curve, all right? So the tangent line is less than or equal to the function's value. I'd probably even take the less than or equal to symbol on a test. Less than or equal to. That means the same thing, all right? Now, sometimes they'll do the reverse in the multiple choice. Let's say you're taking the AP test eventually, and you got your multiple choice, and you've got A, B, C, D, and E. You've got 5 possibilities for every single question that you do on the AP test, all right? So, what if they switch it around? What if they say the local linear approximation is less than or equal to the function's value? What's true about f? Then you would say, oh, concave up. See, we're going backwards now. Oh, if the line is less than the curve that it's approximating, then the curve must be concave up. So you would find the one that says f concave up. So we can also go backwards. I'll probably go backwards like on some of the homework or maybe on the sample test just to test you out both ways there, okay? So that could be an answer. Now I've heard of a couple of years where the AP test did not include f concave up in the multiple choice, but they put something else that was very sneaky that means the same thing as f concave up. So I've heard of a couple of years on the AP test where my students were all ready and they're looking in the multiple choice and they're like, oh no, it doesn't say f concave up. That's not a choice. I better pick another choice that means the same thing. And then they all come back to me and say, we figured it out. One of the questions was f double prime positive. Isn't double derivative positive the same thing as original function concave up as per the derivative test, right? Remember the double derivative test in that other chapter? So that means the same thing. Now they can't put both on the same test. They can put one, but they can't put both. So if you don't see this, circle this instead, means the same thing, okay? All right, that covers 3-1.